Shall we start?
Sure, go ahead.
Okay, okay, great. Okay, transition from the quantum mechanics wave function to the binary mechanics bit function is inevitable. Let me clarify some terminological points. Everyone here is probably familiar with the Schrodinger and Dirac equations, which are sometimes called wave equations. I refer to them here as time development equations, in which the system state is the quantum mechanical wave function. So when we're referring in this terminological point I'm making now to the wave function or the bit function, we're talking not about the explicitly about the time development equations, which I will get into, but we're talking about the system state. The system state defined by the wave function. Can you see my cursor?
Yes.
And the bit function. The wave, okay, let's see, that won't scroll there. So I have to, yeah, that works. Okay, great. The wave function wrongly assumes that physical events at multiple points occur at a single point. This is just an abstract summary of content to come. And events may occur at points in space and time that do not exist due to the belief that space and time are continuous rather than quantized, as in binary mechanics. The wave function, in other words, the system state used in classical quantum mechanics, also fails to adequately represent physical events in the network of concurrent and countercurrent spot unit components of the binary mechanics spot cube spatial lattice. Historically, technologies that work have been generally adopted even before underlying physics is fully understood. The follow the money rule leads directly to exponential increase in binary mechanic technology usage, which improves spatial and temporal resolution by multiple orders of magnitude, as shown below in Figure 1. Required for continuing progress in industries working at increasingly microscopic, quote unquote, nanotechnology scales, and beyond that nano level, by the way. I just use that as the reference word that is sort of a keyword in the media these days, attracting both physicists and capital investment. So here we're talking about some science that might actually get capital investment. So what do we have here? In Figure 1, increased spatial and temporal resolution. The prior technology gives you a temporal resolution. I believe this is near the attosecond level. And spatial resolution, I think this is what you get in the electron microscopy. With BML, Binary Mechanics Lab technology, here are the Keene scale constants, primary constants for time and length, and the improvement is many orders of magnitude better than the current technology. So that's the basic increased spatial and temporal resolution available these days. Background. In the 1994 binary mechanics paper, which was written back in 1994, by the way, first published in 2010, noted intrinsic limitations of the quantum mechanic wave function. Differences in the state vectors, again, the binary mechanics bit function and the quantum mechanic wave function, this is our system state vectors, pinpoint why quantum mechanical formalism cannot, in principle, provide exact results. Why? Namely, it assumes that bits or quanta or one states in binary mechanics, as we'll see a little later, at different physical locations are positioned at one point. This defect remains, excuse me, even if quantum mechanical calculations are conducted at the same fine scale of binary mechanics. This oversimplification intrinsic to the quantum mechanical wave function limits the accuracy of calculations at reduced distances and time duration. This is why I'm saying the transition is inevitable above. It also leads to qualitative paradoxes and discrepancies with experimental observation, similar in nature to those found when classical mechanics was applied at the atomic scale. With the need for increased accuracy and resolution, as multiple commercial industries, we're talking about NVIDIA, Qualcomm, AMD, Intel, these are major companies. This is just in the electronics field, not to mention other industries in medicine and so forth. As these industries probe more microscopic levels of fineness to meet their design and engineering goals, use of the binary mechanic bit function in applications avoids major sources of error in the quantum mechanical wave function. Binary mechanical calculations of physical quantities are, in principle, exact. Therefore, the precision of calculations is limited only by the degree of precision available at the time of measurements used to set the primary constants of binary mechanics, aka the Keene scale. The intrinsic limitations of the wave function may be easily remedied by using the bit function. By the way, I started using this phrase, the Keene scale, because a lot of the crowd in physics keeps talking about the Planck scale, which is complete nonsense. So I thought, well, you know, let's name it the Keene scale so that people can compare the two and see which one they like better. Okay, let's start with figure 2 here with quantized versus continuous position. Let me read some text about it first, and we'll come back to this figure. As presented, well, the topic is incorrect quantum mechanic position values. This is a very serious issue. As presented previously, the quantum mechanic wave function may misrepresent position in continuous real number coordinates, which is on the right side up here, which are only an approximation of actual positions where only integer coordinates are allowed with binary mechanics spatial quantization, top left. How bad is this quantum mechanical defect? Quantum mechanic calculation results may indicate motion when there was none, or may overestimate or underestimate motion distance. What are we talking about here? Let's look at the graphic. I hope that this helps a little bit. Okay, here's your wave function on the right, and the binary mechanics idea here on the left. Here let's say we've got a true position that we're on the x-axis is equal to 1. And over here, we've got our continuous measurements, which will only approximate the true position, which is 1. But, so this is closer to 1 than 0. Excuse me, too much smoking, sorry. This arrow is another measurement closer to 1 than 2, but it's still off, okay? So that the true positions are only approximated. Now, let's look at another situation in row 2, which I mentioned below. No motion from time 1 to time 2, nothing. The measured position at time 1 and time 2 is the same, at 1 in the x-axis. Here we've got 2 measurements, which imply an imaginary motion from time 1 to time 2. And so when in fact there was none. This is a very serious problem of accuracy. Let's go down here to the 3rd row. Here we have true motion is equal to 1 unit of length from time 1 to time 2. But here we are going to wrongly overestimate the amount of this motion. As you can see, the distance between this arrow measurement and the time 2 measurement is greater than 1 unit of length. shown here on the left. Similarly, I think you're getting the idea now of how to interpret this perhaps a little bit cryptic illustration. What if we have, again, true motion, subtracting the position at time 2 minus the position x at time 1 is equal to 1, plus 1. It moved in the plus 1 direction. Here, with our continuous variable real number measurements, motion may be wrongly underestimated. Now, this is a very serious situation. Now, this figure 3 shows essentially the same thing that we showed above. And so we're going to go a little bit fast here. And we can come back to this figure, but it shows basically what was shown above for space, but this time with inaccuracies with respect to when an event occurred. In other words, the quantized time versus continuous wave function time. In the text is similar. Figure 3 shows similar results for time quantization. The QM wave function may misrepresent time in continuous real number coordinates, which are only an approximation of actual time, where only integer multiples are allowed with BM temporal quantization. Quantum mechanic calculation results may indicate time difference when there was none, or overestimate or underestimate these time differences. I'm skipping fast over that because it's very similar to the space situation. QM infinitesimal operators. Now let's go to the time development equations in which the wave function or the bit functions occur as the definition of the initial or system state, which is going to develop over time, as for example, in the Schrodinger and Dirac equations, okay? And they contain what's called, infinitesimal operators, and they're quite simply the wrong math when position and time may have only integer values. There are no infinitesimal increments, okay? In the quantized binary mechanics quantized frame of space and time. Thus, at the binary mechanics finest level, QM predictions may be distorted or outright incorrect. A specific example of this limitation of quantum mechanic formalism was reported previously. This is in the paper where we derived the Bohr magneton constant for the electron. And that's a specific example. As a consequence, success of quantum mechanic formalism at the atomic level is becoming more difficult to duplicate at the elementary particle and nuclear physics levels. Next topic, QM fails to quantize energy. Max Planck, bless his soul, reportedly hoped to quantize energy. This goal was not achieved. However, his milestone contribution defined his Planck action constant H, which is the product of energy times time in units of joules, seconds. Binary mechanics completes this story, defining energy quantization with its equation 1, figure 4 upper. We limit the absolute value of x and y in the complex amplitude to 0 or 1, quantizing energy, so that the M-type energy bit can only equal 0 or 1. It can't equal any other value. No fractional values allowed. Same way with the other bit, which we call the L bit, equals 0 or 1. Full energy quantization may have remained elusive prior to binary mechanics. Why? Due to studies of fine structure energy levels defined by splitting of spectral lines representing atomic configuration changes. Numerous closely spaced energy levels have been observed. Which difference in energy level, if any, might be the BM quantized energy value? It seems the answer may be none. Why? The many closely related spectral lines are probably all averages of multiple events, perhaps even millions, at the BM level of fineness defined by the Keene scale. With this parade of numerous closely spaced spectral lines, it may be easy for us to understand that successful energy quantization was not realized prior to binary mechanics. The general quantum mechanic failure to quantize, which is sort of like a strange thing to even say, because after all, they call it quantum mechanics, don't they? So, but why are they failing to quantize? The foregoing commentary may highlight key weaknesses in QM formalism. Meanwhile, the BM postulates of full quantization provided a basis to discover the Keene scale values, which map directly to the SI units of measurement used in science, namely energy in kilograms convertible to joules or electron volts, as you may like, length in meters, and time in seconds. Without the BM postulates of full quantization, the Keene scale was not even known to exist, much less what its values are. In short, full quantization replaces the long-held assumption that energy, space, and time are continuous. This goes all the way back to the Greeks. And there are four elements. Quantum mechanics fails to define motion. Binary mechanics system state equations 1 through 6, which are in the references, are thought to define an absolute reference frame. We got to think about this seriously, which is required to determine if motion has occurred or not. The Schrodinger and Dirac time development equations strive to define motion in a particular reference frame. However, without an absolute frame, it may not be fully clear if apparent motion is physically real or only a result of the choice of reference frame. This quantum mechanic defect has dire consequences. For example, quantum mechanic formalism does not pin down if an object motion actually happened physically. Hence, quantum mechanics cannot even begin to address the question of the mechanism of motion. Physics is supposed to be about how things work. The author encourages physicists to have more curiosity. For example, Newtonian and quantum mechanic physics are happy to describe motion and leave the question of how things move, the mechanism of motion, for another day. In contrast, biologists, and by the way, they always say that physics is a more, a higher, a better science than biology. Well, I think the physicists have to catch up with the biologists. In contrast, biologists were not content to simply describe the motion of a cockroach across a grid on a chessboard, its velocity, its acceleration. That's what you're going to get from Newtonian physics and quantum mechanics. They wanted to know mechanisms, these dumb biologists. They wanted to know how the cockroach moves. Thus, the sliding filaments of contractile proteins were discovered. The energy source described, the molecule ATP, manufactured in the mitochondria from glycolysis. And further, the neural networks coordinating the muscle contractions. So the biologists are way ahead of the physicists on this score of curiosity of how things work. Since BM defines an absolute reference frame, there's a big payday. Motion can be studied, number one, and its mechanism revealed, and the reference for that work is here. Now the Pauli spin matrix reveal. We're getting into the real cake here. We're getting down into what are the nuts and bolts inside our cake, and we dealt a little bit with the icing. Now we're going to get into it. The Pauli spin matrix set appears in both the Schrodinger and Dirac time development equations, the so-called wave equations. These QM equations have produced excellent results, say, for the electron behavior. Physics literature presents a variety of somewhat cryptic explanations. You may find them cryptic or not cryptic. I'll leave that up to you. of why use of these matrices works to produce results as predicted. Physicists generally agree that rotation of a matrix used in an equation does not alter the underlying physics. This is a key point. Former MIT student James S. Hughes showed that rotation of the Pauli spin matrices produced the 8 vertices of a cube, which subsequent work by the author mapped to 8 elementary particles. It's table 1 in these references. That is, the Pauli spin matrices may be specifying a cubic lattice of these cubic structures called spot cubes. And that's shown in figure 4 above and the lower left, the illustration of a spot cube. In sum, what are we talking about here? What's the goal here? Or the take-home message? With rotation of the Pauli spin matrices, 2 views are permitted and revealed. The original unrotated version and its collection of cryptic explanations, or second, the rotated version defining the 8 vertices of a cube leading to the BM model of space as a cubic lattice of spot cubes. In outdated quantum mechanics, the time development equations might wrongly portray complex interactions among the 8 binary mechanic elementary particles represented in the spot cube as the behavior of a single particle type, such as the electron. In other words, the quantum mechanic formalism may be greatly oversimplifying what is actually happening as far as we can tell. If this is true, the bottom line is that quantum mechanics is simply unable to represent correctly events at the BM level of microscopic fineness. This possible QM fail is a major limitation for continued usage of its formalism in commercial applications. Here enter in the chip companies like NVIDIA, Intel, Qualcomm, and so forth. They're going to need something better than quantum mechanics if they want to stay ahead of the game. In contrast, binary mechanic formalism provides an unprecedented means to achieve substantially greater accuracy and resolution in commercial design and engineering tasks. Here's our last point before the discussion. Incomplete quantum mechanic wave function. QM formalism asserts the so-called uncertainty principle, as I know you're all well aware of that one, as a purported fundamental property of physical systems. In binary mechanics, this QM principle is known as the dumb universe theory, namely that the universe is done, but not the theoretical physicists. One result is that the wave function describes only half of the story, object position or object momentum, not both simultaneously. With this self-imposed limitation, in other words, this is not Jim Keene saying you're limited. No, the quantum mechanics theorists themselves impose this limitation in their own work. Without this self-imposed limitation, the wave function is now obsolete since the advent of the binary mechanics bit function, which demonstrably represents, that's a whole nother talk. What is the demonstrably? How is that done? Represents both object position and momentum simultaneously at any quantized time t, where t is the Keene scale primary constant. Okay, we're almost done. Do we have a few more minutes? This is a very short discussion. Does the dog bark? This article outlines a tsunami of bad news, sorry about that, for quantum mechanics and its wave function. With the limitations and defects briefly listed, and yes, I was very brief above, the reader might wonder why quantum mechanics formalism is used at all some 15 years after the first principles of binary mechanics were introduced. What works the best? This is what wins the game, both for theoretical physics and in the real practical world. What works the best? Historically, technologies that work have been generally adopted even before underlying physics is fully understood and before all debates among physicists have been resolved. In other words, binary mechanics is not going to stop physicists from debating things. For example, electron microscopy provides useful images of atomic configurations. Solid state people love electron microscopy to show how the atoms are organized structurally in solid materials and other materials. Its practical real-world utility stimulates its widespread usage. Although quantum mechanics theoreticians continue to discuss what the electron actually is, its size. Is it a point particle, for example? Its shape and composition. Likewise, one might expect increasing and considerable demand for quantum technology advances based upon binary mechanics first principles, while physicists continue to discuss and explore fundamental questions and the scientific merit. Licensed for physics, binary mechanics technology advances may be licensed to users and packaged as a collection of software tools, including the time development engine. In other words, like for example, for 3D video games, they talk about the rendering engine that takes the data and renders it in a 2D image. By analogy, we're going to use the same term, image and software engine, for the time development of a system state in the universe. And these tools also include setup of initial states for any physical system, capture of frame-by-frame state changes for analysis, and many more. For example, consider a cesium 133 atomic clock, where a single tick cycle occurs in approximately 10 to the minus 10 seconds. With the present quantum technology advances, this interval amounts to a whopping almost 4 to the 10 to the 13 frames, documenting the exact sequence of events in the cesium 133 clock cycle. Just one of those 9 billion? Let's see, million. Yeah, that's 9 billion ticks. Okay, just one of those ticks. We've got almost 4 to the 10 to 13 frames documenting the exact events during which an electron is thought to transition between hyperfine energy states. Investigators can study what actually occurs, much like film or video may be examined frame by frame to view and learn details of the events recorded. I remember on social media in the last year or so, with the assassination attempt in Pennsylvania of the US president, people were gathering videos and looking frame by frame in these videos to find details of what was going on. Okay, and there's another, perhaps even greater payday available. Once key events are better understood, as described above here, factors changing clock rate may be studied. You know, we talk about GPS and the clocks are slower up in orbit than they are on the Earth and all of this stuff, such as factors which might change clock rates, such as temperature, pressure, energy density, and altitude, comparing clocks in orbit or on Earth. This is the big payday. In addition to understanding and studying the process, we can then do experiments as to what changes the process and learn a great deal. This is just one example of how binary mechanics technology might produce both practical and scientific advances. At present, a selection of BM software tools are freely available in the hot zip file which one can download with this link. Play for the win. The follow the money rule may lead directly to exponential increase in binary mechanic technology usage. I've noticed, for example, in the last months, a huge increase in views of the binary mechanics website, which improves spatial and temporal resolution by multiple orders of magnitude, as shown in Figure 1. Required for continuing progress in industries working at increased microscopic scales, attracting both physicists and capital investment. So here we're talking about a case where both physicists and theoreticians might have some interest, and also the money men. To be competitive, binary mechanic technology may be a required resource at academic physics departments. For example, to get the very best, brightest students, if your physics department at Harvard, Yale, MIT, Caltech, wherever, over there in Britain or Germany or wherever, if you don't have on board the resources for the faculty and students to use binary mechanics technology, you're not going to get the best and brightest students in your physics department. And in the US national labs, in addition to numerous commercial enterprises. End of story. Thank you very much for your attention.
All right, Jim. Well, all right, we got 5.5 minutes.
Good talk, James.
Thank you, Rick.
You're welcome. I would like to say, though, it's cesium and tsunami. The T silent.
Tsunami.
Tsunami. The T is silent.
And what is the pronunciation? The other one says Ian?
Cesium, Adam.
Oh, cesium. We're going to seize up here. Okay.
Yep.
Cesium, Adam. Cesium.
Well, that's a pretty
otherwise awesome stuff.
That's what happens when you live on an island and you're not talking with people every day, you know.
Okay, I think we've asked this question before. What's the M and the L refer to in if you go up to your picture?
Good question. The M and the L are referred to mites and lights. Those are just two sort of crazy names I gave to these two types of one states, you know, the mite bit and unfortunately that this was actually prior to discovering the Keene scale, where we've got M, L, and T as constants, but these are in italics in all of my papers so that it's sort of consistent distinction, but perhaps these could, you know, this is the bit that defines color and electric charge, and this is the bit that defines momentum and direction.
Okay, so not to be confused with mass and length.
Exactly. It just I named them, in the original paper, I named them mites and lights, and for example, in the unconditional bit operation, the M bit moves to to this locus. The M bit radiates an L bit, you might say, and these are in a C sequence. So you can imagine another spot unit there. The L bit would then in this shift to the right in the unconditional bit operation. So the L bit becomes the carry bit, and it becomes an M bit, so that the lights materialize as mites. And all of that was before the Keene scale was even developed and defined. And so we use M and L and T in there. And so, but so good question. And it's unfortunate, perhaps, perhaps I should, you know, but I don't want to go back and change all the papers, you know, because, but maybe I should use a little M and a little L or something like this, not the capitals or whatever. But that is a point of possible confusion, I admit.
Would this be representing motion?
Yes.
In a way, yeah.
Yes. In other words, the the bit function is actually the collection of these M and L bits. And that's what the bit function is. And it contains information about future motion. And these L bits are also possibly the long sought after magnetic monopoles, okay? The M bits represent the electric field and the L bits represent the magnetic field, okay? And so that each one of these locations, if they're in the one state, in many of my illustrations, I make it a black circle or a black arrow to indicate the one state. But this is just an illustration of the position of these quanta, or these locations that contain one state or zero states. The zero states, of course, are the neutrino field. Combining both of these together, you get the total energy field. And so, yeah, in a way, binary mechanics is a field theory in that sense. It defines four fields: electric, magnetic, the sum of the two, which would be the energy field, and the one's complement, which is the neutrino field.
All right, less than a minute to go here.
Does the L bit only, or so the M bit only move in one direction?
Yes, it moves in the direction of that the L bit is pointing. By the way, this is not only a spatial object containing one states or zero states. It's actually a machine which implements the time development equations of binary mechanics. So this is machinery here we're looking at. We're not just looking.
Okay, so we didn't, so we only used up 40 minutes. I'm not sure we're going to have a lot of discussion and commentary here. So I've approved you. You can put your presentation back on. So I think the big issue in my mind is this business of the uncertainty principle and determinism. Does binary mechanics get rid of the problem that quantum mechanics is non-deterministic? It looks to me like binary mechanics is deterministic and quantum mechanics is non-deterministic. Is that a correct way of phrasing it, Bob?
Yeah, that's,
Yes.
I mean, it's very hard to give conclusive evidence, for or against determinism. So that I wouldn't even take as a criticism necessarily that it's deterministic.
Well, thank you, Robert. I find that in a way physicists opine about this a lot, and they're saying, well, this would mean that people don't have free will and so forth and so on. In my opinion, the physicists attempting to take the determinism in binary mechanics and extrapolate that to whether people have free will is completely a bogus step from one place to another. But that's the way it goes, So also the so-called Bell inequality. I'm trying to position this to the here, the incomplete, the purported uncertainty principle. But the Bell himself said that this inequality would not apply if things were deterministic. And that's about the first thing he says in the famous paper on the Bell inequality that everyone cites.
Yeah, what I think it really shows is you need a special reference frame because you have something that's like action at a distance.
Exactly, yeah. And so, yeah, so but by the way, Ian, I'd like, Ian mentioned a paper that the uncertainty principle might be, there might be some evidence that it's not as exact as the delta x delta p equals h over 2 pi or whatever it is. The uncertainty principle, the way it's written down, could be a little bit off.
Well, I think it's kind of messed up in more than one way. Heisenberg originally stated it in terms of knowledge, but you can also try to state it in terms of properties of waves and particles, where you take like a Fourier transform between a wave and a particle, for example. But there actually are counterexamples. I know, like Popper, he had a thought experiment, but it turns out they've even shown it experimentally, where, like with paired particles, you can show the position of one and measure the momentum of the other with more exactitude than is allowed under by the uncertainty principle, and then they try to find various ways to hang on to it. It's one of these cases where you can hang on to any principle if you're willing, to change enough other things. But personally, I think they ought to just give up on the Heisenberg uncertainty principle.
Yeah. With that said, it I think it reinforces my allegation or commentary that the wave function in quantum mechanics is now obsolete, since it only can represent half of the story, object position or object momentum, but not both simultaneously. The bit function does that. It represents both simultaneously.
Well, I actually wrote a comment. Excuse me. Good presentation, by the way, Jim.
Thank you, Jerry.
Well, okay, I wrote.
You all don't have to be so kind. You can tear me up too.
I really enjoyed it.
Thank you.
Okay, cool. Okay, with the uncertainty principle, I've always questioned it. The momentum of a particle implies its position, such as, if you see it in motion, that's where it is. That's its position. So why couldn't they always know why couldn't they always know each when they know one? I've heard, though, that electron microscopes, that the light or photons can alter the position of the observed particle. It doesn't say anything about the part. If so, this doesn't say anything about the particles themselves, only our means to observe them. I don't know if this is what they arrived at through the I don't know if that was what it was intended, but I've heard that, though.
I agree with what you're saying, Jerry, that this uncertainty principle really may refer to the limitations of measurement that we have. In other words, the technology that we have to determine momentum or position at a very fine microscopic scale. And so it's more a methodological limitation than a theoretical constraint.
Yeah, the grain of truth there is if you shorten up the wavelength, the energy increases. So you try to measure something with a lot of precision, and you're going to affect it greater because the energy of your particles higher.
Right. So
that doesn't mean it didn't have smaller properties. It's just that we can't learn about them.
Well, sometimes you can only observe a thing, not measure it.
Well, observing is a measurement. I'm not sure the distinction you're making there, Rick, if you want to clarify that.
Well, like if you want to physically measure the distance something travels, sometimes the only way you can do that is through observation. You can't set up a sensor that's small enough to detect a single electron without, again, affecting that electron. But
Correct.
through visualization, like through visually seeing, you may be able to see that electron in motion if you have a way to visualize the electron without interfering with its motion or its being.
But how are you seeing it without light? And light, of course, is going to affect
Well,
it.
the only thing that, or we don't know anything that's smaller than the electron, so that's the limiting factor there.
Well,
Actually, there's a recent finding by Long Ju, that's Long space Ju, a researcher at MIT, claiming to have shown and publishing in Nature in the last year, I think, that a fractional charge in the electron. For actually decades, fractional charge has been purported to exist with regard to quarks, as I think everyone here knows, but not for the electron. Binary mechanics, right out of the gate in table 1 of the 2010 paper, predicted the fractional or 1/3 charges comprising the elementary charge in the electron. And just in this last year, the Long Ju work from MIT has been interpreted to support the idea of the actually observing fractional charge movements in this. It's sort of a material science study, but they were surprised to find that the amount of charge being detected moving between the layers or parts of their experimental setup were 1/3 of the elementary charge.
I wouldn't be surprised because of the fact that we now know that 2 photons will create an electron. Perhaps it's maybe more than 2 photons. Perhaps it's 3 photons.
Well, that's one of the unifying features of binary mechanics. Binary mechanics doesn't tell you what things are. They just say we got some space, and in that space, we're going to have some one states, some stuff there. You can think whatever they are. I call the one states quanta. And so that what it boils down to is that whether you're talking about light or electrons or protons, whatever you're talking about, it's got to be quanta is what you're really talking about. So light is not something different in its composition or its constituent components, shall we say, which are one states, than the electron or the proton or anything else. So that's one unifying concept in binary mechanics. It's also quite liberal that you can come in and say, well, I think the one states are this, that, or the other, and binary mechanics is not going to contradict you. You're good to go. You can think they're whatever you want them to be. But binary mechanics doesn't really answer that question yet. And so that's sort of a liberal point there. Another thing about this quantization of charge, including this recent finding confirming after some 15 years from the original paper in 2010, that the 1/3 fractional charge of the electron, I mean, this is a major league advance and from this lab at MIT. And those people who talk about smearing the electric charge in toroid shapes and other spherical shapes or whatever have a lot of explaining to do. But binary mechanics is just fine because the experimental results seem to agree 100% with the basic foundational principles and equations. But those of you out there that are thinking that this charge can be smeared into some spherical shape or toroid or whatever, I think you've got some problems with this quantization of electric charge and fractional electric charge, now shown in the electron. Sorry for such a long speech.
I was just wondering, generally, conventionally, I suppose the failure of integrating, accepted theories, quantum mechanics and general relativity and so on, what they say is, oh, well, on the large scale, general relativity applies, and on the small scale, quantum mechanics applies. Now, nevertheless, I suppose if you push them, they would probably say, well, if you're really observing at the very small scale with electron microscopes, you're affecting the wavelength of what you're looking at and so on, and that's when the effects become obvious. But I suppose if you push them, they'd probably say that the product of the uncertainty in the momentum and the position of a universe, a nebula, let's say, would still must be greater than or equal to h over 2 pi. So I suppose I'm wondering in a way, Jim, would you say that binary mechanics applies at every scale, or is it more a microscopic scale as well?
Yeah, I claim that this. I have no reason to say that it doesn't apply at every scale, and this is the cosmological relevance here. In other words, the best theory of physics, some people call it a theory of everything, is required for a viable cosmology. And right now, according to many people, a lot of cosmological work is based upon theories which, in fact, have been excluded. My own work excludes in two different papers using different methods of lunar laser ranging and also the GRACE satellites, the twin pair of GRACE satellites that were trying to measure gravity. So that's a theory that's been excluded by the data, not my data, the data that this French observatory collected with lunar laser ranging and the GRACE satellite data. Now, there's also the GRAIL satellite data, where they put a pair of satellites around the moon. Now, to do the same thing, to map gravity, so to speak. What I think they were in fact mapping, as I showed with the GRAIL satellites, with the GRACE satellites around Earth, that by the way, this whole idea of having these twin satellites was concocted precisely by the general relativity theorists, okay? And after my paper, anyway, I bet you those same theorists don't even show their face at NASA anymore because it's so embarrassing, because what they found is that they were measuring seawater temperature. And I've indicated that temperature, surface temperature, is an important factor in the law of motion to move the moon closer to Earth during full moon. And so the whole idea of people using theories that have actually been excluded, not theories that are sort of in question or on the drawing board, but have been definitively excluded by real world data as a foundation for a cosmology, is completely bonkers.
Well, in my view, you don't need a unified theory to understand the cosmos, because it's been portrayed as this unalive, dead thing that, just moves because of gravity. You apply the electric force to the universe and the cosmos, you see these Z pinches as galaxies, and within the galaxies, these Birkeland currents present as smaller Birkeland currents, creating suns, and then you have Birkeland currents from suns connecting to planets, which have been proven by Christian Birkeland, that last part, that the sun has a direct connection and NASA has mapped these so-called flux ropes in space that go directly to the sun from the Earth, and same with Saturn, same with Jupiter. Any planet that has a magnetic field has these Birkeland currents directly connected to them. And everything is interconnected in the electric universe, from the atom all the way up to the cosmos. The Z pinches that are the universe or galaxies don't need any dark matter to be held together, because it's an electric phenomena, a pinch phenomena, and the rotation is because of Lorentz force.
What
And
is Z pinch? Z pinch.
A Bennett pinch.
What is a Bennett pinch?
A Bennett pinch is where, when you run current through an area, the magnetic field that's created pinches that current down and confines it, and energy, it like puts lots of energy. So if you put a pop can in the middle of this field, it'll crush it instantly. And Bennett is the fellow that discovered this phenomena.
Okay.
Anyways, go ahead, guy.
Gary says you need to give us a presentation about all this. And you're welcome.
Okay.
I did have some questions about the Jim, about these gray satellite, GRAY, is that correct?
No, it's
Great.
Grace, GRACE. And the idea was that these satellites would discover, as it were, increased mass below the surface area, which would cause a greater gravitational signal, which they detected. What the GRACE satellites, in fact, detected was surface temperature, as predicted by binary mechanics, as important in the gravity phenomena. It's not a force, it's just a collection of phenomena that people group together. Now, there's a similar concept with the Grail satellites, and those are
okay. So Grail satellites. Now you're talking about two different things. That's what's confusing me.
Well, the GRACE satellites were orbiting Earth, okay, and that's downloadable data, which I downloaded and analyzed and presented. The Grail satellites are orbiting the moon, and the idea is that they want to find massagons, or what did they call them?
Massagons.
Concentrated mass
Right.
Below the surface of the moon. And what they, in fact, are probably finding, if their results are similar to what the GRACE results were, they're finding areas of increased higher temperature on the surface of the moon. Now, I downloaded all this Grail data, and I think temperature measurements are in there, and so that one can analyze this data to confirm the results that I got with the GRACE satellites orbiting Earth, which would confirm this. By the way, my analysis of the lunar laser ranging, I think, can be confirmed by data from other observatories, a number of other observatories, which have long-term data on the lunar laser ranging times and indicating distance. And so I wonder whether no one has published a confirmation of my study there, or whether they did it and found that my study was right, and they said, well, let's just hush up about that because it destroys relativity, general relativity.
Okay, let me clarify a few things here. The GRACE, GRACE satellites, apparently there are two of them, is that correct?
Right, and they're based upon general relativity thinking and calculations, and
Okay.
they hope to define concentrated mass. I guess more dense rock material um, below the surface of the Earth, and what they in fact found was increased temperature.
Okay. Now the Grail, Grail, is that right?
Yes, it is the same idea, twin satellites orbiting the moon, and their data is also downloadable. And they were aimed at the same idea of the gray satellites for Earth to find concentrations of mass below the surface of the moon. I think they call them massagons, or I forget the term that
Mascons.
yeah, which are probably, if one analyzed the data, if temperature is included in those downloads, one might find that their mascons are really just warmer areas of warmer surface temperature in agreement with binary mechanics predictions.
Okay.
And therefore excluding general relativity. You notice they haven't
right.
put up any more of these satellite pairs.
Surface or interior?
Perhaps they're well aware of my critiques and studies which rule out general relativity completely.
James?
Yes, sir.
Surface or subsurface? Because you were saying subsurface before, but they're
They're
finding that
looking
this.
for mass subsurface, Rick, but what is relevant to binary mechanics is surface temperature, because that creates thermal radiation, and where the surface temperature, say, of the moon is greater when in full moon facing the Earth, more quanta are in the environment between Earth and moon. And the
Well,
law
that
of
makes
motion of binary mechanics says that objects move toward greater quanta density. And
right.
so
Well, that
that's
makes
why
sense because the solar wind is impacting on the moon all the time. And, electrons bumping into, particles of mass that are on the moon will dislodge other electrons or change the atomic structures of the particles on the face of the moon. And
well,
that would
I suppose
result
the
in heating.
solar wind is affecting the Earth and the moon together. But what my study on the law of motion is that because one side of the moon is warmer, there's more radiation, and objects move toward higher quanta densities. That radiation, thermal radiation, produces more quanta on the bright side of the moon than the dark side. So when the bright side is facing the Earth, the moon moves toward the Earth. And that's some 10,000 kilometers of motion. This is not just some little nudge. This is a major motion, and general relativity does not predict this, because according to general relativity, the overall temperature and energy of the moon is more or less constant. It doesn't matter what the phase of the moon is. There's no reason to think that the moon would move closer to Earth during full moon compared to away from full moon. So
Well,
general
I
relativity
have a question.
predicts no result, but there is a result.
Jim, is
Yes.
it possibly because when the Earth is positioned to where it receives the full moon, it's on the other side of the moon, and that might affect its gravity from the sun, because when it's on the other side, you know the way that the Earth and the moon affect each other's gravity, they sort of wobble around with each other. I mean, at some level, I mean, it's mostly the moon revolving. However, though, if the moon is on this side, the Earth is right here, and the sun's over here, it would seem to affect the gravity that might pull it a bit closer. That's just a thought.
Well, the orbits are very, when you delve into it, the orbit of the moon around the Earth and the Earth, all of the orbits of all of the planets and their moons are very, very complex. when analyzed with respect to Newton's law of gravitation, which is circular. And it turns out that mass is only tends to be correlated with the effect seen, but how is a particle in the center of the Earth going to affect where the Earth moves, or in the center of the moon affects where it moves? Tell me that. You can't. What is actually affecting and recognized by astronomers is radiation pressure. Radiation pressure from the sunlight, and you talked about these solar wind and so forth. That's going to push the planets away. Well, what is going to move them toward the sun so that we get some kind of an orbit or a constant distance from the sun? That's the law of motion of binary mechanics, where the warmer side of the moon, let's say, is going to, the moon will tend to move in the direction of its warmer side. And just like the Earth is going to move in the direction of its warmer side, just like the Pioneer satellite that they sent out years ago has an anomaly with respect to its position. And what is that anomaly? The anomaly is that it tends to move toward the direction of the sun, its warmer side. Why? Because the bit density, the quantum density is greater on that side, because the heat being radiated from the surface on its warmer side. So that what you have with binary mechanics is a consistent theory that makes some logical sense and also intuitive sense, whereas the Newtonian idea that mass is the key. By the way, all of these masses of these planets and everything else in the universe is all inferred mass. We haven't weighed the moon on a scale or the Earth on a scale. The Cavendish experiment tried to do that and more or less got let's just say that was a pretty good estimate. Okay. But from that type of estimate, the mass of everything in the universe comes. It's all inferred. We have no idea what the mass of the sun is. We look at the orbits and say, well, if Newton was right, then the mass of the sun must be X. We have no idea what the mass of Jupiter or Saturn are. But we look at the orbits and say, well, if Newton is right, then the mass must be such and such. Kilograms. It's all circular logic. Plus, it's also non-intuitive logic. How is iron in the center of the Earth core going to affect anything with respect to the motion of the Earth? Tell me how. Does anyone have any inkling how what's going on there physically? I've heard no explanation for that, but everyone accepts the idea that somehow magically you've got some stuff in the center of a planet and it's going to affect its orbit. Well, how in the world would that happen? Astronomers accept the idea of radiation pressure. They're tracking this incoming Atlas, what is it, the CI Atlas interstellar object, which is approaching our solar system right now. There's a lot of controversy about what that object actually is, because it has some very strange properties. and they actually use radiation pressure in their calculations to determine its trajectory, our expected trajectory. As it gets closer to the sun, it's going to experience more radiation pressure from the sun, which should deflect it a little bit away from the sun. So astronomers use the ideas that binary mechanics promotes. But certainly the idea that a bunch of iron in the middle of the Earth or in the middle of Venus or Mercury has anything whatsoever to do with its orbit is really crazy stuff. I mean, how would that happen? Is there little messengers coming out from the iron bottle?
Ions. So do you have gravitons and binary mechanics?
Nope. Oh, that's the nice thing about binary mechanics. You say, what does binary mechanics have? It has one states quanta. That's it. It doesn't have anything else. If the graviton exists, it must be some pattern of one states. Okay. And so you could say, I have this pattern of one states, and I'm going to call it or name it a graviton, much like I have done to with the proton bit cycle and electron bit cycles to define those two particles by their cycles. That one states tend to revolve around a circle, creating intrinsic angular momentum in those particles, and that's how and we're going to name them a proton and an electron. So that if you want to ask, does anything exist? Tell me like say the Higgs boson. The first thing I said and I wrote some papers on this, when the so-called Higgs field came out, the first thing I ask is, well, what's the bit function for it? How do you define the Higgs boson? Give me its bit function. Where, what is the configurations of one states at any particular time, or the spantal temporal pattern, a sequence of bit states, if you want to define to me the event that you're calling the Higgs boson. It turns out that the math of the Higgs boson is quite similar, or Higgs field is quite similar to the math I showed in figure 4 in today's presentation, where the complex amplitude, it's two complex amplitudes. Well, what is that? Those are adjacent spot units within the electron where transfer can occur and give mass to the electron. So that they sort of were close with respect to their math. They just didn't follow through and sort of break away from the crowd and say, let's just do this. They had to hold back to be consistent with the other guys that were so far behind.
Jim.
Yes.
According to the Keene scale, with the quantization of space, like how large is one unit, say, compared to a particle such as a proton?
Well, let's see. Let's go back. Can you see my screen?
Yeah.
I'm going back to figure 4, wherever it is. Okay, how big? The proton is approximately the size of the spot cube. Okay, that's how big. How big is L? You notice that the radius of the spot cube is approximately 2L. So how did I home in on this value for L? Scattering data from way back in the 20th century showed that the proton had a radius of about 1.2 or 1.3 in that area femtometers. So I said, gee whiz, I've got the proton bit cycle, which is approximately the size of this cube, okay? And I've got scattering data from laboratories of people who know how to shoot particles at one another and measure the trajectories and the way they scatter, the angles of scatter, and calculate what the size of those particles must be, namely, in this case, the proton. And they're saying it's 1.2, 1.3 femtometers radius. So this must mean that our L value here, L, or, here's the L value. There's about 2 from the center over to the edge. And so we get the Keene scale value of about 2/3 of a femtometer for the L constant. Once you've nailed that down, by the way, other data, more recent data, if you look up proton radius on Google, like I did a few days ago, will claim that the proton radius is about 0.8 or 0.9 femtometers, smaller than what I'm saying here. Okay, but they use a completely different method to determine that, and I have to look into what that method is. But it's not scattering. Okay, so it's based upon electromagnetics or something else. Oh, okay. So this is a story which requires a lot of smart people to do stuff. Okay, there's plenty of questions to raise and to answer, but to answer Jerry's question, which was how did I arrive at the length in the Keene scale? Was that the question, Jerry?
I was just asking what the size of a proton is. Well, they say
Right,
electrons are
about the size
almost,
of this spot cube. Parts of the proton bit cycle extend beyond the spot cube into neighboring spot cubes, which is the whole key to how multi-Z atoms occur or develop, because excess energy in any spot cube is going to disperse where? Not just anywhere. It's going to disperse to neighboring spot cubes. So then you get entities of a higher Z.
All right, we're going to run out of time here.
Okay, thank you for your chairmanship, Harry.
All right, we got less than a minute, so it should cut off here pretty quickly. All right, why don't you resume and talking about this? Okay, Jim, you were interrupted there. Sorry about that.
I think I more or less finished my point. I guess to summarize, the view of orbits and planetary motions and the motions of moons and so forth is portrayed in binary mechanics, to bring the cosmology into it in a more realistic fashion. The radiation pressure from the sun will push planets away from the Earth by the momentum carried by that radiation. This is something that astronomers accept the concept. They accept the concept and they use it in actual calculations of objects such as spacecraft and incoming interstellar objects, in this case that I mentioned. So what's the other half? Why don't these planets and the moons and so forth just keep blasting away from each other? Well, the thing that draws them together is the binary mechanics law of motion, which means that objects tend to move toward greater quanta density. Obviously, the side of the object closer to the sun, getting all this radiation pressure, is going to be warmer. It will radiate more. So therefore, the quanta density on the side of any planet or a moon in our solar system facing the sun is going to have a greater density of quanta than the side away from the moon. And the law of motion simply says that objects move toward greater quanta density. So we have two sides of the story. We have the solar wind, or what's called the radiation pressure, moving objects away from the sun, and the resulting temperature rise on the surface of objects. This is why the surface is important. Who cares what's going on in the middle of the moon or the middle of the Earth? It's irrelevant what its temperature is or anything of that nature, because that temperature will probably conduct to the surface on all sides of the Earth, more or less equally. So that it's irrelevant what the temperature at the core of the Earth is. What is relevant to the law of motion is that on the sun side, the quanta density is going to be greater. And so the Earth will tend to move toward the sun for that reason. So you need the law of motion to be added to the radiation pressure, which astronomers already accept and use in their calculations. And we're good to go. Don't need mass at all. The mass of the
Okay.
Earth may be of interest for various scientific purposes, but certainly not to explain gravitation phenomena.
Oh, so you're going after the Newtonian as well as the Newtonian gravitation as well as general relativity.
You got it. Yeah. And in the paper, my latest paper, which I read today, and thank you for your kind attention, everyone. I very much appreciate that. Yeah, I explicitly mentioned Newtonian physics, and I've given papers or presentations here about that, and its universal gravitation is really a major mistake. Unfortunately, mass has to do with size of the planets, and so it's correlated with gravitational phenomena. And the size is important because that's the area, what astronomers call the disk area. It's not a disk, it's a sphere, but they call it the disk area. I'm not sure why. I would call it the hemispheric area receiving sunlight. But anyway, they call it the disk area. Is greater if you got greater mass. So mass is correlated to the orbits, but it's not in terms of the physics of why the orbits are what they are, is not directly related. And in fact, all these masses that you read about, you can go Google all the planets and Wikipedia and so forth, and they give you the mass of the planet and whatever, and it all agrees with what the orbit properties are and so forth, and everything is in its proper place and so forth. Well, it's also circular logic. They get the mass from the orbits. And then they say, if Newton's law is right, then the mass must be this. Then Newton's, and by the way, this idea of the fact that the mass is only correlated with the phenomena observed agrees with the fact that the reduced number of significant figures in the capital G gravitational constant.
See, this argument, it's an interesting point you make, Jim, about circularity of reasoning. I think that could be applied to any scientific theory. I mean, in the case of, say, Newtonian gravitation, one does some experiments and one finds that one can formulate a theory based on mass and gravitational constants and distance and so on. And then when it becomes accepted, as you say, one can say, well, look, since this orbit is observed to follow this pattern and the radius is such and the speed is such and so on, therefore the mass must be such and such, if Newton's theory is right. But I think that could be said about any theory. We're quite aware of the circularity of reasoning in modern physics and maybe relativity. You've now interestingly applied it to classical physics. Well, I dare say, with respect, one could probably apply it to binary mechanics as well, if one looked into the detail. Once one has accepted a theory as being explanatory, well, then one does extrapolate and engage in some circularity of reasoning by saying, well, look, if this theory is right, then these are the consequences of it.
Well, I would be most thankful. I think Ian has made a very important point, and it would help me a great deal if you all would read any of the papers and point out problems, point out where maybe I'm just going around in circles, where there might be logical inconsistencies. I would love that. Because I've made some claims which some might find a little bit abrasive, and I don't mean any harm, but it's true. So I would love, like if someone could point out, this is circular logic here, and therefore the claim that this binary mechanics moves our understanding from point A to a better point B is really not valid, and on a particular item or overall, however it might be. So thank you, Ian. This would be most welcome um, to receive. In fact, I'm sort of struck by people maybe too polite. I would like to see some critiques of binary mechanics. Some people who looked at it very closely, I won't name names. I'll let them speak for themselves when and if they want to, but have not found any logical inconsistencies in binary mechanics and have said so. So, but I'd like, it can't be. I've even revised things. If you go back, that's why I don't change the papers too much. Sometimes I do some updates on some papers. That's what a living journal on the internet can do. You can update a paper. I usually indicate that a paper has been updated so people know that it's a little bit different in some respect than before. But I revised the truth tables for the scalar and vector potentials and forces some years ago and published a paper titled that these are revised and were revised. And so, so that really nothing is exactly written in stone as far as I'm concerned. I did the lunar laser ranging study quite early. If you look at the date, it's 2011, I believe, immediately, because the law of motion, which seemed to be one can deduce from the basics of binary mechanics, seemed so fantastic. I wanted to disprove it. And the lunar laser ranging from this French observatory actually confirmed the result. So I failed to disprove my own theory in that case. But I would like to see other critiques or fallacies or needed corrections that would be most welcome. I would be very happy, and I would not be offended in the least.
I would think that if you went to Physics Stack Exchange or one of these mainstream sites, you'd get lots of argumentation. Or perhaps publishing at VIXRA. I notice there's a lot of comments on papers at VIXRA where people say this guy's an idiot, particularly this guy, Jorma.
Well, that's ad hominem. That doesn't help anybody.
Well, you're asking for criticism. Usually the criticism is
not ad hominem criticism. I already know that I'm a bastard.
We're right and you're wrong because we say so. That's usually what the criticism boils down to. We're right because we say so.
So you're saying that the theories are so bad that these people have that they can't even come up with any substantive critique.
Well,
that's a good point there, Harry. You've really nailed it there. You've crucified all of these people because they apparently can't even make a critique because they don't have the theoretical machinery to do so.
Yeah, well, you're asking, you're asking for some critique, and I'm merely pointing out that there are places you could go and get critique. It might not be useful critique. It might just be smoke and mirrors.
Well, I'm interested in useful critique, like, for example, the binary mechanics lab simulator could be used to determine X, Y, or Z if it were set up so that we have this experimental condition and this control condition, and what do we get? And maybe the person actually does the experiment and shows that it gets something which is contrary to some of the principles of binary mechanics.
Well, Jim, I guess you know that I'm skeptical of your theory. I mean, I'm skeptical of so much. So
well, that's fine.
Well, no offense or anything, of course. But
I'm skeptical too. So that makes two of us.
Well, as far as the atom goes, would you say you accept the classic structure where the electrons revolve around the nucleus like planets?
No,
or something entirely different? Okay.
One of my programming tasks is to actually do bit function analysis to identify atoms and the associated electrons and what their positions actually are and how they change over time. And so that's an upcoming need, programming need in binary mechanics. And a lot of this requires money, okay? Because time is money. I only have a limited amount of time. And I'm smoking enough that I'll probably might even be dead tomorrow. So, so there's plenty of opportunity for people to make their mark.
Yeah.
Well, I think that's a pitch to the wrong audience here. I mean, we're not young physics people, you know, guys at 20 years old in college. That's would be my thought on that. I think that's really your audience. And would be my view.
You
Does that
could be
sound
right.
right? Yeah. So the question for your point of view is, how do you get the attention of young physics students, or people who are looking for new ideas in physics?
Well, we definitely need a publicist, and I have a feeling that I've said this before here in this forum, that I think the younger generation is more internet savvy than some of us older guys, and that the increased traffic at the binary mechanics website is like may reflect that to some extent, that younger people are saying we can go out and find stuff ourselves and not be so beholden to what our professors say. And then, of course, the professors are going to have to catch up, because they notice that in order to get these students, or even to address questions that these students may raise in class, they're going to have to study a little bit of the source material in order to respond effectively.
Okay, so as a summary, then I would say that your idea, your concept of binary mechanics not only invalidates general relativity, quantum mechanics,
Special relativity
physics,
also.
particle physics, the three big areas of physics. But so you're invalidating all three of those paradigms.
And
Plus,
classical physics.
We're not necessarily throwing away all the results of those different areas, but certainly the full quantization postulates are the ones that, you know, when we talk about special relativity, we talk about Einstein's two postulates about the speed of light and the equivalence principle and so forth. Well, these full quantization postulates are the ones that are the big ones in binary mechanics. And yes, it's a major change in approach and thinking. And I wasn't even thinking about this stuff until James Hughes popped up in my kitchen, because we both had some mutual friends. And he was working as an electrical engineer at Ford Company, testing their electronic stuff in their cars way back in the 1980s and 90s. And he showed up saying that he rotated these matrices, and he knew that I knew matrix algebra and had programmed, principal axis factor analysis, matrix rotations, and all of this stuff, and really understood the math. And so he presented this on my blackboard in my kitchen, and I'm a nut enough to have a blackboard in my kitchen at that point in time. And I was sort of amazed and said, well, you know, if the rotated matrices are pointing to the vertices of a cube, the big question is how far apart are these points, in the cube? You know, that's turned out later to be our length constant, L, italic L, capital L. And so I thought that's a number we really would need to know, wouldn't we? And Hughes had no idea. But, you know, it seemed like I couldn't find any error in his math. And in fact, in the 2010 paper, I did my own matrix rotations of the Pauli spin matrices. There's a whole section showing that you can rotate them easily to get 0 or 1 out of each of them. In other words, and each one is associated with an axis, X, Y, and Z. So you got X, 0 and 1 in the X-axis and the Y-axis and also in the Z-axis. What do you have? You've got the vertices of a cube. And these are the matrices that everyone's been using, and in some respect, with great success, the unrotated original Pauli spin matrices. It turned out they don't have anything to do with spin whatsoever. They have to do with the cube. And so I'm not sure what question I'm addressing, or am I just rambling? I think I'm just rambling, but that gives a little color to how all of this got started. That I had to ask the question, well, okay, how far apart are these vertices? You know,
my point was that this, you were talking about my comment. My comment was we have, and I'm simplifying this, but we have 3 large paradigms of physics. We have particle physics paradigm, there's the quantum mechanics paradigm, and then there's the general relativity paradigm. And from what I've been reading, people criticize those paradigms by saying they don't really fit together at all. So there's no fitting together of the main paradigms of physics. They don't create a logical structure that's consistent. So they're just separate, as Bill Lucas says, silos. They're separate areas of physics that have their own assumptions or postulates, if you will, that they derive from. And yeah, I guess there's some overlap, but that they don't really fit together. That's kind of what I'm getting when I look at papers that are critical of the current paradigm. Go ahead, Roger.
Yeah, I've got a question. So, trying to struggle through this. When we were talking about the light speed earlier, what is binary mechanics saying about one-way light speed and two-way light speed? Is it saying that both of them are variable, one of them constant, or what?
Well, I did a study using the binary mechanics simulator, Roger, showing that it appears that the light speed in 2 directions. I did unidirectional light speed in 2 different directions, and opposite to each other, right to left and left to right, in the binary mechanics simulated volume. And the light speeds were, for all practical purposes, the same within, random variation in the data. So that we have, and by the way, light speed is not the maximum speed. It would be bit velocity, which is pi times light speed.
So you're saying the two-way light speed is variable, or?
I'm saying that in my measurements of one-way light speed, unidirectional, the 2 speeds appeared to be comparable or the same. In other words, indistinguishable in terms of what I called the front velocity. And there's a paper on that called light speed derivation.
So you're saying the one-way light speed is variable, or is it constant?
No, that both are not variable. Well, both were the same. Let's put it this way. Both were the same under the conditions of the experiment. And so it turns out that light speed depends upon a number of things, such as the density of the media that, as
normally deal with in vacuum.
It slows down light speed.
Yeah.
So what I did is I tried to get as close to vacuum as possible by making the initial conditions to be absolute 0 Kelvin. Okay. And then a gun would shoot quanta or light signal in one side, which of course would raise the temperature of the volume as you're shooting energy into it, and then measure the arrival of quanta on the other side. Now, at 0 Kelvin, there is no arrival of quanta on any side because you're at zero Kelvin. Things don't move at 0 Kelvin.
Okay,
So,
thank you.
yeah.
I just wanted a quick, easy answer. Is one-way light speed constant, or is it variable? Is two-way light speed constant, or is it variable? Okay, thank you.
It's variable.
What is two-way? Two-way light speed is variable, and one-way light speed.
Well, the one way in both directions appear to be about the same, which would mean that, but they both can vary depending upon other conditions such as quanta density or energy density, and that's refraction. You know, if the light's traveling through glass, it moves slower than it's traveling through air, right?
Yeah. Okay,
Okay.
But were
relative.
these conditions
Thank you.
in a stationary position, or did they take into account the movement of the Earth?
Well, the nice thing about the binary mechanics simulator is, by definition, you're simulating an absolute frame, and so there is no motion with respect to the Earth. So that whatever you're doing there is in the absolute frame defined by the bit function, which is the initial state that you're working with.
So that's why perhaps you gave that answer to Roger, you know, that you got the same answer basically, whether it was left or right. But I think he might have been trying to
Exactly.
tease out what would happen if you had a non-absolute system. Would you get a directional dependence on the? He was asking about one way and two way, but I'm just concerned about you know, the measurement of the speed of light in a non-absolute situation.
Well, you see, that's an excellent experimental question. Probably some upgrade or additional programming would be required to do that sort of a simulation. But again, it's a worthy question that you ask, Ian, and that's the way things go. You know, like the binary mechanics simulator started out as um, you know, a laboratory piece of software. It didn't necessarily have to be beautiful. It just had to be correct in what it was doing. And I later wrote an interface program, which is a GUI, graphic user interface, like we're used to with Windows programming, for example, and Linux programming too, which allows you to set up experiments, but it's all in an absolute frame.
Jim, if I may try to recap what Roger was asking, at least I think, are you familiar with the one-way light velocity debacle, as far as, you know, when a light source bounces off a reflector and receives a sensor, you know, whether the light traveled one distance and then back, if they're the same, like if it's maybe 75% one way and 25 the other, or some configuration, like if there's an ether and light travels in a fixed way relative to the ether.
Well, I've had a moment to think. I think you're asking the same question that, or you're raising the same scientific problem that Ian just raised, if I'm not
Yeah.
mistaken.
Yeah.
And just thinking in the few moments since Ian raised that point, maybe I responded by saying, hey, some additional programming is necessary. But look at it this way. In the frame, in a moving frame with reference to the absolute frame, definitely the light velocity in the two directions would be different. Would they not?
I don't know personally.
Well, I mean, if they're the same in the absolute frame, but now you're going to be moving along to the right or the left in that frame and following the same data, wouldn't it then appear that the light is traveling faster in one direction than in the other?
Yeah.
Well, Einstein arrived at the synchronization convention to settle that, of course, with I think it's
Yeah.
1905 paper.
Okay, let's sort of I guess the big question here is does so would you say that binary mechanics creates a an ether type of space time?
Yes, the spot cube lattice is in fact the binary mechanic definition of what people have previously thought of as the ether. But in addition to just simply being a lattice of these spot cubes, one has to realize that these spot cubes do things. The individual spot units do things. They implement the time development equations of binary mechanics so that one can now what the ether is not some passive thing. It's actually a huge machine which is running the universe. Okay.
How does
Yeah.
light actually work with binary mechanics? How does light travel and such through spot cubes and such?
By the equation 7 through 17 of time development equations, that they tell you exactly how light moves.
So they take up a unit as they go through space. Like they occupy units like 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 particles.
Well, I don't know what you mean by units of particles.
You know, like the spot cubes, like they occupy spot cubes, or their signal is one, just as mass takes up spot cubes and makes them one. Is that correct?
Makes them one. What do you mean by one?
Isn't that what you call one? Like it's either one or zero. Like a spot cube, it's either filled or it's empty. Isn't
Well,
that?
the spot cube has let's see, some 40 or so in individual locations, bit loci, so that there are, like for the proton bit cycle, there are 2 to the 42 different configurations.
Oh
For all
wow!
the
I
hadron
thought you had
particles.
said that it's either filled or empty. I thought you had said that before.
That what?
Sorry. I thought you had said they're either filled or empty. I'm sorry.
Yes, no, right. I mean, a particular bit locus is either in the one state or the 0, 0 state at any particular time.
Okay.
Do the cubes move within the frame?
No, the
They're
cubes are the frame.
stationary?
They
Okay.
are the frame.
All right.
Okay, we have any more questions? We only got like 8 minutes here. I'd like to make some comments. So anybody else?
With respect to what Harry was saying about the 3 theories of particle, quantum, and general relativity. For some reason, he left out special relativity, but I throw that one as a 4th. One might
that's absorbed in special relativity is absorbed in general relativity.
As you wish, fine, no problem. One might think as a detective and say, what's the common ground for these 3? They all are based upon the theory of continuous space and time. And binary mechanics breaks with that assumption. So it's like, like a detective, a homicide detective might think, what does these different crimes have in common? And what they all have in common is the belief that space and time are continuous, that real number math is the way to go, and it works just wonderfully. There are no more significant remaining questions to be addressed, and so forth. Binary mechanics, James Hughes ruined everything for me by pointing out his rotation of the Dirac spinners, or the Pauli spinner matrices. And so ever since, I have broken with that, with all of the theories based upon that false assumption of continuous space and time. So it's a completely new scientific paradigm that we're talking about here. It's not just a tweak of any of the existing ones.
You mentioned these cubes are frames themselves, but what I'm talking about is in a larger frame of reference, do these cubes move within that larger frame of reference, say our scale?
Well, the spot cube matrix, if you will, includes the entire universe,
Yeah.
the entire known universe. So
Mhm.
your question then becomes, what is beyond the known universe? And I don't have an answer to that. I don't think anyone does, else it wouldn't be the
No, I was just
order of the
asking
known universe.
whether these cubes wave within our frame of reference to allow electromagnetism to propagate.
I think they're all
No,
fixed and
they're
stationary.
thought
Because
to
if
be
you're referring to
stationary.
it as it's being referred to as a possible ether. Well, we know that
They're
electromagnetism flows
they're
along
not
something.
an ether in terms of particles being a medium and waving around. No,
Okay.
they're a fixed frame.
Okay.
What moves are the one state quanta. That's
Yeah.
what.
Yeah. I got you.
Okay, any other questions here? We got 7 minutes, 5 minutes.
Thanks,
I
James.
did want to ask
Thank you, Rick.
Ian a question. This guy Jormoka that I sent you, is he going to give a talk?
Oh, this was the one you sent me, Harry, was it?
Yes, the guy from Finland.
Yeah. Oh, okay. So, first of all, you give me someone's this Marco Pereri or something. It bounced back from him. No email address, valid email address. The other one I think you're talking about, he hasn't come back to me.
The one that you said that you were that I thought you had affirmed up a time with this Finnish guy, Jormuka or whatever his name is. I don't know how to pronounce it. The Finnish
Yeah.
guy.
No, I think he's the one who hasn't replied to me yet. I'd have to
All right.
I'd
Okay.
check
So,
it. Yeah.
all right. I did want to point out to Jim that the Jormuka guy, I'm not even pronouncing it correctly, he says that general relativity is wrong. And the reason is when he tried to quantize space, he couldn't get it to agree with general relativity. So you might want to look at his paper. Now, I did send out links to that.
What is the spelling of that gentleman?
Jormamal. It's in the email.
Jorma.
John Milka or something like that. It's a Finnish
Yeah.
guy.
Yeah, just do a
Okay.
search within your email, James. You should be able to find it just from a few
All right.
letters.
Anyway, the point is,
Well, a lot of those emails I just delete
all
because
right, the point is, we don't have much time. The point is that he says that general relativity is wrong. And the reason is because when he tried to quantize space, he couldn't get it to work with general relativity, which kind of, I think you need to take a look at that.
well, I think that's a bit. I agree. That's an important piece of work.
Right.
It supports the binary mechanic approach, at least at a general level. That showing that the two things are not compatible with each other.
Well, that's kind of my understanding of reading his work, that he kind of has abandoned general relativity and says that the whole thing is bunk and nonsense because he couldn't make sense out of it when he tried to quantize space, and which looks like he's in attempting to, um, unify general relativity with quantum mechanics. People have been trying to do that for a long time without much success. That's a major problem. Okay, so we got 2 minutes and 30 seconds.
I may have to correct what I said because he possibly has accepted. I'm just checking now. There were three people you gave me details on, Harry, and let me just check now.
Well, the first one was this Finnish guy. He's Finnish. I don't know how you pronounce Finnish words.
Yeah, I beg your pardon. That man is giving a talk in November.
Okay, all right, that's what I
Yeah,
thought.
he
Okay,
is. Sorry, it's the others I couldn't get any joy from.
okay, so we should be
November
hearing
8th.
from him at some point in the future, and that should be interesting to you, Jim, and you can ask questions about that if he talks about that particular aspect.
Yes, sir.
Okay, we do need people to talk, give presentations. I want to thank Jim for stepping up and giving a presentation this week. I'm kind of working on why general relativity, paradoxes in general relativity. And that's kind of an interesting subject. But in the process of doing this, I've discovered new paradoxes in special relativity. So that's always fun. So I don't know if you want to hear about that next week. If anybody else wants to step up, that would be appreciated.
Well, that sounds interesting, Harry. Also, there's the mystery of why there are no paradoxes in binary mechanics. Where did they all go?
Well,
So we have the
probably
case of the
because,
mysterious missing paradoxes. They're all gone.
well, that's probably because the mathematics is self-consistent as opposed to problems in these other areas of physics where I don't think the mathematics is self-consistent at all. When you get down to the nitty-gritty where they're accused of being self-consistent, they deny it. And the vociferousness with which they deny it, they point to experiments prove it's correct. So they don't actually address the incorrectness of the mathematics. They shift gears and say, well, the experiments prove that the theory is correct, so therefore it's correct. So that's a kind of a dodge. You see what I'm driving at here?
Yeah, and it introduces a good criteria for a wrong theory